Why is Ohm's law in neurodiagnostics important? I can touch a 12-volt battery. It's a marine battery with more than enough charge to kill me many, many times over. But hey, I can't even feel it. But I think we're about to see some sparks. Yeah. A simple knowledge of Ohm's law would have easily predicted what we just saw.
Within the physics of electricity, one of the firm pillars of the foundation is Ohm's law. Why? You may not realize it, but every moment you have a patient connected to your neurodiagnostic equipment, you're using it. You're using Ohm's law. It applies to every part of your setup. By the end of this video, hopefully you will understand more about current, voltage, and impedance, including the components of impedance, the resistive, capacitive, and inductive components, as well as know the difference between impedance meters and ohm meters and when it's appropriate to use each. First, we need to explain some important underlying concepts, including steady state, capacitance, inductance, and magnetic forces. Steady state, what do we mean by that? Steady state in electricity simply means constant speed. As we will see later, this specifically will mean steady state electrical current. But thinking about cars helps visualize the concept. This car is going slow, but a steady 20 miles per hour. This car is going faster at 55 miles per hour, and this car is cooking along at 90 miles per hour. Are any of these speeds constant? Of course they are. All three are. They're different speeds, but they're staying constant at whatever speed they're at. What about this car? Is it at a constant speed? Absolutely. It is not moving, but the speed is not changing either. It is at a constant speed of 0 miles per hour. Non-steady state, of course, means that the speed is not steady. The speed is varying, accelerating or decelerating, whether starting from a stop and speeding up like this, stopping after going fast like this, or stop and go. All of these cars are accelerating or decelerating, changing speeds. They are not steady state. Remember the term steady state. Anytime the speed is changing, it is not steady state. Capacitance. Capacitance is simply the ability to store or hold charge. Our skin and hair are very good at holding a charge.
A capacitor holds electrical charge the way a bucket fills up with water. It can only hold so much. Once it's full, it can hold no more, regardless of the size of the bucket.
This is a large capacitor from an old gas power supply. What's on the inside and what does it do? Having a look at how we could create a capacitor like this will help us later understand how capacitance impacts impedance. Let's start with a circuit we can all relate to with lead wires attached to our patient. We're going to zoom in on the red wire and remove a section we will soon put back. Here's a thin metal plate. Let's add to that a thin film of electrically non-conductive material, something like paper, polymer, ceramic. Finally, let's add another thin metal plate to sandwich that non-conductive film and connect the lead wires back to each side of the metal plates. We have just created a capacitor. It's called a capacitor because, hint, hint, it has the capacity to hold electrical charge on the charge storage plates. And just like the bucket, it's just waiting to be filled. Next, inductance. When I move this magnet near our recording wires, we see that a current is generated in the wires that establishes a voltage on our amplifiers. This happens because of Michael Faraday's wonderful law of electromagnetic induction. Now, let's look at this magnet. It has an associated magnetic field with magnetic flux lines, a few of which are shown here. If we surround this magnet by a coil of wire like this and move the magnet back and forth, a voltage is established due to electromagnetic induction. Electromagnetic induction induces a voltage in the wire coil as the magnetic flux lines move through the wire coil. How about magnetic forces?
If you got a set of magnets handy, grab them. We all know that magnets can repel like this. You go that way. Or magnets can attract like this. Opposites really do attract. The physics of these magnets are very, very similar to electrical charges, as we're about to see in a moment. However, there's some important characteristics to consider right now. Zero potential energy. Separate the magnets, we have potential energy. And when I release them, it's going to become kinetic energy, back to zero potential energy. Potential energy, about to see kinetic energy, taking them back to a state of zero potential energy. Now back to Ohm's law.
Ohm's law defines the relationship between electrical voltage, current, and impedance. Here is Ohm's law in all algebraic orientations. We can solve for current with the symbol of I if we divide voltage, symbol V, by impedance, symbol Z. Let's move that equation up. Switch sides, please. And some algebraic manipulation shows that we can solve for voltage by multiplying current by impedance. Switch sides again, please. And more algebraic manipulation shows that we can solve for impedance by dividing voltage by current. What are these variables? What are voltage, current, and impedance? Let's start with voltage.
Remember how we said these magnets are very similar to electrical charges?
Opposite charges attract. When the barriers are released, the opposite charges quickly move under the force acting on them to come together, and similar charges repel, whether negative charges or positive charges. Opposite charges always seek to stay together in their low energy state. Just like the magnets, they do not want to be separated. In the same way it takes energy for this dude to force his weight upward, it takes energy to force joined magnets or opposite charges apart. In summary, we know that when the opposite charges are together, they have no potential energy. And when they're separated, they have potential energy. Another name for that potential energy is electrostatic potential. We have created an electromotive force. The most common terminology is to say that we have created a voltage. And when we double a charge, we've doubled the voltage. Any guess as to what current is? Current is a measure of how much charge is flowing. If we release the charges, they flow back together. We just had a current flow and there is no more voltage. Charge flowing, that was a current flow. Let's create a voltage. It takes some muscle to separate these charges, but we got it done. We have created potential energy, so we have a voltage. A lot like this battery. The battery uses electrochemical processes. It uses those processes to separate the electrical charges into two electrical poles. There's a positive pole and a negative pole. You could think of the battery as having a small electrochemical engine, like this one shown. You can see that it keeps those charges separated.
So the little engine inside is working to keep the positive charges here and the negative charges here. There is no pathway for them to return on the inside because the engine's getting the job done. But what about on the outside? Can air conduct electricity?
Yes, but air doesn't have freely moving charge particles. Often over 100 million volts are needed to force air to conduct. That's an enormous amount of energy. That huge voltage essentially ionizes air particles, allowing the flow of current, the lightning strike, between the atmosphere and the earth.
So in essence, the electrical poles are trapped. The positive and the negative are trapped at their location without a way back to each other.
But what if we introduce a silver wire between the poles? As soon as we touch both the positive and negative poles with the wire, we get a current flow of negative charges from the negative pole of the battery flowing where? Towards the positive pole. Why? The negatively charged, freely moving electrons are repelled or pushed by the negative pole of the battery, and they are attracted to the positive pole of the battery. Yep, current and voltage really are just that simple.
Many of you likely know these neurodiagnostic stimulators or others like them very well. Are the voltage producing engines inside of these more complex than the electrochemical engine inside of this battery? Absolutely, for sure. But the physics and interactions via Ohm's law here are just as simple as they are here. I can assure you that when these neurodiagnostic stimulators create a voltage, it's as simple as separating opposite electrical charges, and when the charges flow back to each other, we have a current.
Let's do a quick summary of voltage and current. The tiny electrochemical engine inside of this battery separated the electrical charges into a big pile of positive charges and a big pile of negative charges. That established a positive and negative pole. That's potential energy. Or we could say electromotive force. Or we could make it easy and simply call it voltage. And when the silver wire was connected, there was a pathway for electrons to move in a direction to release the potential energy inside of the battery. The potential energy turned into kinetic energy. That was a current flow. Do you think that kinetic energy of the current flow could do something? Yes. This car had an enormous amount of kinetic energy when it stopped, or more appropriately, when it crashed into the car that it ran into. The energy it released is obvious. Hopefully, our current's kinetic energy can do something very useful, like power a flashlight. The bulb of this flashlight is going to work as long as the electrochemical engine of the battery can keep the charges separated to keep the voltage in place to drive the current through the wire. But what if the battery dies? If the electrochemical engine inside of the battery stops being able to keep the charges separated to establish the voltage, the battery charge will quickly drain and the current will stop since the voltage dropped to zero. So no more potential energy means no more kinetic energy? Exactly. No more voltage means no more current.
An analogy between electrical voltage and current with a set of magnets. In case you didn't know, the attraction equations between magnets like these are almost identical to the attraction equations between opposite electrical charges. Imagine, this is a bunch of positive electrical charges, and this is a bunch of negative electrical charges. When our opposite electrical charges are together like this, they have no potential energy. They have no voltage. If we separate the opposite electrical charges, we get potential energy. We have voltage. And if we have a pathway for them to get back together and release them, we get movement. We convert the potential energy to kinetic energy. We have a flow of electrical charges. And guess what? We just witnessed a current flow.
It is a simple yet elegant relationship that exists between current and voltage. Hopefully it's all starting to make sense. But what about impedance? Once again, magnets will help us understand. For this simulation, the magnets flow easily through the air. But what if we place toothpaste between the magnets? It's a little harder for the magnets to move as quickly. As the magnets come together, displacing the toothpaste is not as easy as displacing the air. The toothpaste clearly impeded the movement or the flow of the magnets coming back together. We could say that regarding the flow of magnets back together, the toothpaste has higher impedance than does air. It's no more complicated than it sounds. For instance, this little guy is impeded from running around. Why? Because he's standing in a basket. He looks pretty determined. The training wheels on this little girl's bike impede her from falling over. When we bring the concept of impedance back to our electrical circuit, we know that current flows very readily through this nice heavy silver wire, so we can assume it does little to impede the flow of current. Or we could say that the silver wire has very little impedance. And if we have an opening in the silver wire with an air gap like this, our current flow completely stops. We could say that the air gap has near infinite impedance to current flow. The silver wire would be as good as we could ever hope for. Silver has the highest number of freely moving electrons of any metal. It is the most electrically conductive metal, or we could say that silver is the lowest impedance metal. Carbon fiber wire is often used in our lead wires for neurodiagnostic electrodes and cabling. However, carbon has far fewer freely moving electrons than does silver. If we replace this segment of silver wire with carbon wire, the carbon wire would have to be much larger, with 220 times the cross-sectional area of the silver wire in order to have the same impedance. We could say that for a given size wire, carbon wire has 220 times higher impedance to current flow than does the silver wire. Because of this, the most common material used to make electronic resistors like these is carbon. So from now on, we will call this carbon segment a resistor. Remember how we said there are three components of impedance: the resistive component, the capacitive component, and the inductive component? Let's create a circuit with all three of those. We can already guess that the resistor represents the resistive component of impedance. Remember our capacitor? The capacitor in this circuit represents the capacitive component of impedance. Remember the concept of inductance with the magnet? The inductor shown here is identical, except that the core inside of the coil of wire here is simply a piece of iron. The inductor in this circuit represents the inductive component of impedance. The stage is set with our three impedance component players. How will each of the three different components of impedance respond to supply voltages of different frequencies? Best to look at each separately. What do you think will happen when we connect the wire to complete the circuit? Remember that the capacitor feels like the water bucket. As soon as we connect the wire to the battery, current flows and our capacitor begins to charge. Once enough current has flowed to charge the capacitor to the exact same voltage as the voltage on the battery, no more current flows. We could say that the capacitor has completely blocked steady-state current flow. If we exchange our zero frequency steady-state voltage source, our battery, for a non-steady-state voltage source, one with a low frequency like we have here, what can we observe? The capacitor quickly builds to a near equal voltage to the source voltage and allows only a tiny amount of current flow. You have to look closely to even see the electrons moving. The current is so low. We could say that the capacitor has greatly opposed or impeded low frequency current flow. Let's increase the frequency. The capacitor is charging to a lower level of voltage. In addition, the capacitor is allowing a larger amount of current to flow. What happens if we use a high frequency supply voltage? The capacitor is barely charging. The voltage building up on the capacitor is very small, and the capacitor is allowing a very large current flow. We could say that the capacitive component of impedance did little to impede high frequency currents. Next, let's move to the inductor. Here is the inductive component of impedance with our steady-state battery as source once more. Remember how the inductance was able to generate a voltage? Let's be on the lookout to see if it does so again. When we connect the wire to the battery, the inductor does nothing to impede the flow of the steady-state current. It doesn't even have any voltage develop on it. It's a little bit like the inductor isn't even in the circuit. When we replace the steady-state battery with a low-frequency non-steady-state voltage source, there is a very small voltage that builds on the inductor. Why? Because the inductor opposes any change in the rate of current flow by establishing a voltage that opposes the source voltage. In this way, the inductor impedes current flow. Though the current flow is not impeded much at this low frequency, that's a hint. A low frequency has a low rate of change in current flow. Hint, hint. Do you think that higher frequency current will be opposed more by the inductor? Let's increase the frequency. The voltage on the inductor has become larger with the result of impeding current flow more. What happens if we use a high frequency supply voltage? The voltage on the inductor has grown to the same voltage as the source voltage. The inductor has impeded current flow completely. That brings us to the resistor representing the resistive component of impedance. Let us assume the resistor shown has much more resistance than the conductive silver wire. When we connect the wire to the battery, a current flows and the source voltage builds on the resistor. And guess what? This does not change no matter what the frequency of the source voltage is. Whether low frequency, medium frequency, or high frequency. An important note, the resistive component of impedance affected current exactly the same regardless of the frequency of the current. We could say that the resistive component of impedance did not change with changing frequency. Now that we understand more about the frequency responses of each of the three components of impedance, we can look at our circuit with all three. Let's again start with a zero frequency steady-state voltage. So what's going to happen when we attach the wire? If you guessed that current would flow until the capacitor charged up to the same voltage as the source voltage, you are correct. No more current. The capacitor completely blocked steady state current. When we transition to the low frequency non-steady state voltage, the capacitor impedes current and dominates a circuit by building up a voltage near equal to the supply voltage. Increasing to the medium frequency shows that both the capacitor and the inductor have mildly opposed current flow, leaving enough current to establish a medium voltage on the resistor. And when we transition to the high frequency, we see that our inductor is dominating the circuit. It establishes an opposition voltage identical to the source voltage that effectively blocked all current. Enough of the electrical circuits already, right? Let's back up and contemplate an alternative way to consider the frequency responses of the three different components of impedance. So we have the capacitive, resistive, and inductive components of impedance. Let's imagine there are three separate highways, and we have four different frequencies that need to travel down the highway to get from the left to the right, including zero frequency, low frequency, medium frequency, and high frequency. Reviewing what we have already seen, the capacitive component of impedance treats the different frequencies in different ways. To the high frequency, it says, let her rip, open highway with no attenuation. To the medium frequency, it says, gonna let you pass, but you gotta attenuate a bit. To the low frequencies, it says, whoa, buddy, barely gonna let you squeak through. You have to attenuate a whole bunch. And to the steady state frequencies, it says you are not gonna pass. The resistive component of impedance treats all the frequencies the exact same way. If the resistance is low, everybody come on, highway is open, keep it moving. Minimal attenuation needed. If the resistance is medium, bring it on equally, but attenuate some for us. And if the resistance is high, keep it moving, keep it coming, but attenuate a bunch for us. The inductive component of impedance is the mirror of the capacitive component of impedance. Get a move on. The zero frequencies get a free pass through the inductor without being blocked in any way. The low frequencies are attenuated a little bit. The medium frequencies are attenuated significantly. And the high frequencies are blocked completely. Let's summarize the big picture. High frequencies are treated differently by the different components of impedance, passing freely by the capacitive and being attenuated by the resistive, but being blocked completely by the inductive. Medium frequencies likewise are treated differently by the different components of impedance, being attenuated by each but to different amounts. Low frequencies are also treated differently by the different components of impedance, passing with minimal attenuation by the inductive, being attenuated by the resistive, but being attenuated greatly by the capacitive. And finally, the steady state frequencies are also treated differently by the different components of impedance. The capacitive blocks the zero frequency completely. The resistive attenuates the zero frequency the exact same as attenuated the others, and the inductive did not attenuate the zero frequency at all. What are some take-home points? How can we ever bring an end to our discussion on Ohm's law and ohm meters versus impedance meters? In truth, we could spend weeks discussing this. Let's try instead to keep it real simple here. The supply voltage, the generator of our circuitry, is important, most important. We have seen how we garner different responses when we supply our circuit with steady state voltage like the battery versus non-steady state voltage like this alternating source we've looked so much at. You may already know, or your spidey senses may have guessed it earlier, but the ohm meters or resistance meters use that battery to power the resistance measurement circuit. And the impedance meters use a non-steady state supply voltage to power the impedance measurement circuit. As we have seen, our signals are treated differently depending on their frequency when our circuits include the capacitive and inductive components. And the physiologic signals, the stuff that we're trying to record, has many different frequency components. Consider frequencies you know well: delta, theta, alpha, beta. What about EMG with frequencies that can be in the hundreds of hertz? And don't forget EKG, which is an important signal to be able to distinguish. It is very clear with a cursory look that there are many different frequency components of the EKG. We need to be able to see all of those in order to distinguish EKG artifact when it's present. Most materials have some degree of capacitance and/or inductance.
Most of the things around us have some degree of capacitance and/or inductance. In reality, almost everything has some level of both, even if it's infinitesimal. For instance, plastic, we know what's about to happen. We can easily build up a charge and static charge, it's holding a charge. Capacitance, that's why I was wearing these rubber gloves. Pair of pliers, metal, guaranteed to have inductance, plastic coating, throwing in some capacitance. Cell phone, plastic tube. This big honking thing of stainless steel wire, guaranteed to have a lot of inductance. Lead wires. This is just an EEG cup electrode lead wire. We saw earlier where we were able to electromagnetically couple with a magnet to induce voltage in our recording circuitry, inductance. But most of all, our skin, our patient's skin, has plentiful capacitance, the ability to hold a charge. In the wintertime, every time you get shocked touching your car, it's proof of how plentiful capacitance is in our skin, in your patient's skin.
Measuring resistance on tissue does not work.
2 fresh hydrogel electrodes. They're very old, they're probably dry, but they've never been used. Fresh patch of skin, sandpapered, clean, debris gone. When I apply these on tissue, there's likely a good deal of capacitance, the ability to store charge between that electrode and tissue. When I use this resistance meter, watch the resistance value creep up. Why is it doing that? Because that capacitance is charging, because this has a battery in it. We can never use that to monitor this. We have to use an impedance meter.
The impedance of a circuit is frequency dependent. We best measure impedance at frequencies of interest.
Inside of this impedance meter is a voltage source, a supply source. In the same way that inside of this ohm meter, this resistance meter, there is a supply source, a voltage source, a battery. The difference is that in the impedance meter, the voltage source, the supply source, has a frequency. Albert Grass, being the very wise man that he was, knew it was important that when recording the impedance of this physiologic tissue circuit, it was very important to measure at a frequency that was sort of in the middle of all of the physiologic signals of interest. So he chose 30 hertz.
Measuring resistance is a handy way of checking if an electrical connection is intact.
But hey, don't be down on ohm meters. They serve a very important purpose. For instance, monitoring the integrity of our lead wire. There's an EEG cup electrode, and we can use the ohm meter to measure the resistance, which is 1.1 ohms. So the lead wire on that EEG cup electrode is intact, but that's not measuring impedance. Does that lead wire have some degree of capacitance and inductance? You bet. Would the impedance of this lead wire be different at maybe 1,000 hertz than the resistance value at a steady state DC voltage? Yes, it would be very different. But all we're doing is checking to see if our lead wire is intact. So in summary, the impedance meter must be used for measuring something that has tissue. However, checking to see whether our lead wires are intact, you can use an ohm meter. Well, I hope that this information has been helpful towards connecting the dots. We covered many of the basics about Ohm's law. In addition, we talked about ohm meters, resistance meters, impedance meters. what are the differences between the two, and what are they useful for? When should you use them, especially within a physiologic circuit consideration? From my experience, as well as my friends in neurodiagnostics, I know that quizzes can really help, especially if you have an upcoming board exam regarding the electrical topics such as Ohm's law. So we put together a set of quizzes, and you can find the link to those in the description section below this video. Thanks so much for watching, and if we've earned it, please subscribe.